Okay, before I start, we are aware of the problem with Kaggle. The deadline is supposed to be 4 p.m., but in the setting it was 4 p.m. in a different time zone. So it got closed before the deadline. Since it's Kaggle website, the control is not in our hand. We are in contact with Kaggle to see if there's any way to resolve the problem. How many of you are affected by this deadline?
Professor, it's already reopened on Kaggle.
Okay, is it reopened?
Yeah.
Okay, good. Because first they said that we can't reopen something that has been closed, so it's okay. So if it's reopened, the plan is to extend the deadline a couple of hours for those who have been affected during this period, so everything should be fine. Don't forget about due date for your proposal for final project. There is a Google document in Piaget. There's a link to it with a specific format that you can introduce your project and your group members. The description of project could be very short, 1 paragraph, 2 paragraphs maximum. And that's just for the purpose of knowing the group, knowing the number of projects and the title of and concept of project. And you're going to receive some feedbacks from me whether or not it's an appropriate project for this course. Okay, in the previous lecture, we start learning about support vector machine. So the scenario that we were following was hard margin support vector machine. In hard margin support vector machine, our assumption is that the classes are linearly separable. And we are talking about a case that we have only 2 classes. In a 2-class problem, suppose that data is linearly separable. The plan is to find a linear classifier that can make distinction between these 2 classes such that this decision boundary has maximum margin to each of these classes. So if hyperplane is beta transpose X plus beta null, then we learned that margin of this hyperplane would be 1 over beta. So if you want to maximize the margin, we have to minimize this quantity. So we end up with this with this optimization problem that we would like to minimize, say, L2 norm of beta, subject to the constraint that yi beta transpose xi plus beta null is greater than equal 1. So we learned that we can set or we can rescale this beta in a way that points at least are 1 unit away from the hyperplane. So the minimum distance is 1. So margin is 1, basically. You know, in this case, we would like to, from all hyperplanes, that their beta has been rescaled in a way that the closest point to them is at least 1. We are looking for the one with maximum beta, with minimum beta. This is going to give us maximum margin. So this is the optimization problem that we have to solve, to find beta and beta null. But instead of solving this optimization problem directly, we are finding the dual of this and basically solve the dual of this optimization, dual of this objective function constraint, which is an easier problem to solve. Okay. Let me write the Lagrangian for this problem. You know, this is my objective function. This is constraint. I can form a Lagrangian, which is a function of my primal variable. My primal variables are beta and beta null. And I need to define a Lagrange multiplier. Let's call it alpha. So Lagrangian would be 1/2 beta squared minus, there are many constraints here. If I have n points, for all of these n points, for all xi, I have a constraint. So basically, there are I equal 1 to n constraints. Alpha I is my Lagrange multiplier times yi beta transpose xi plus beta null minus 1. Okay, that's my Lagrangian. And of course, Lagrange multiplier should be greater than equal 0. Okay, if I take derivative of this Lagrangian with respect to my primal variables, beta and beta null. If I take derivative with respect to beta, then I have 1/2 beta squared. It's going to be 2 times 1/2 beta. So basically, this norm is beta transpose beta. So it's quadratic. When you take its derivative, it's going to be 2 times 1/2 beta, which is beta. So this is beta. The derivative of this one with respect to beta is beta. Then what do I have here? I have alpha I, yi, beta transpose xi. If I take derivative with respect to beta, what will be the derivative for this term? Alpha I, yi, beta transpose xi. Its derivative with respect to beta is sorry? It's alpha I, yi, xi, right? It's linear. I'm taking derivative with respect to this. So it's going to be basically minus, and I have a sigma here, alpha I, yi, xi. That's derivative with respect to this term, alpha I, yi, beta transpose xi. I have another term here, which is alpha I, yi, beta null. If I take derivative with respect to beta, it's going to be 0, right? Because it has no beta in it. Alpha I, yi, beta null, take derivative with respect to beta would be 0. And I have a term here, alpha I. Again, if I take derivative of that with respect to beta, it is 0, right? So they want me to expand this. Maybe it's more clear. This term is basically 1/2 beta transpose beta, this norm, minus I have a term in the form of alpha I, yi, beta transpose xi. So beta transpose can come here. And I have a term in the form of alpha I, yi, beta null, when beta null can come here. And I have, there's a, beta. And there is a term of this form, alpha I, this last one. So derivative with respect to this one is alpha I, yi, xi. Derivative of this one is 0. Derivative of this one is 0. Okay. So if I take derivative of Lagrangian with respect to beta, that's my derivative. And this should be equal to 0. So it implies that beta is equal to alpha I, yi, xi. So this is the relation between my primal variable and my dual variable. relation between alpha and beta. Okay. If I take derivative of Lagrangian with respect to beta null, another primal variable that I have. So derivative of first term with respect to beta null is 0. Derivative of second term with respect to beta null zero again. Derivative of third term with respect to beta null what is it? Sum of alpha I y I. It might be trivial, but if you don't tell me, I'm not sure that you understand that it's trivial. So the derivative of the last term with respect to beta null is 0. So this is equal to 0. So I know that alpha I y I for I equal 1 to n is 0. If I take derivative of Lagrangian with respect to dual variable, I get the constraint back. So I don't need to do that. Okay, so let me replace beta with alpha I y I x I in the original cost function that I have. So for any beta, I just put alpha I y I x I in this Lagrangian. Actually, I would like to rewrite my Lagrangian based on my dual variable. You know, because I have relation between primal variable and dual variable, I can write the Lagrangian in terms of dual variable. So if I rewrite Lagrangian based on dual variable, it's a Lagrangian which is not based on primal variable anymore. It's based on dual variable. It's going to be 1/2 beta transpose beta. So I can replace beta transpose with this, and I can replace beta with this. But let me do it one by one. I don't replace beta transpose. It's beta transpose times beta. My beta is alpha I y I x I. And it's minus that was basically this term. Minus beta transpose, the second term, minus beta transpose sigma alpha I y I x I minus beta null sigma alpha I y I. But I know alpha I y I is equal to 0. Right? So I don't need to write this term. It's 0. And the last term is minus alpha I. Okay? Can simplify this. I have 1/2 beta transpose alpha I y I x I minus beta transpose alpha I y I x I. So it's basically these two terms is minus 1/2 beta transpose sigma alpha I y I x I. And the last term is just alpha I. Okay, now let me replace this beta transpose with alpha I y I x I transpose. So it's going to be minus 1/2 sigma alpha I y I x I transpose times alpha I y I x I. Right? So I can just change this I to j, for example, and write it in this form. It's alpha I, alpha j, yi, yj, xi transpose xj over all I and j. So I have two summations here. Okay, minus sigma alpha I. This is my Lagrangian in terms of alpha I. I don't have the primal variable here anymore. It's just based on dual variable. But alpha was my Lagrange multiplier. This should be greater than 0. And I use this when I wanted to simplify this. I use this fact that alpha I yi is equal to 0. So I have a new objective function here with two constraints. Actually, this alpha I minus 1, this should be plus. And this should be plus. This should be plus. So this is my optimization problem now. My optimization problem is alpha I minus 1/2 alpha I alpha j yi yj xi transpose xj subject to the constraint that alpha I is greater than equal 0 and sigma alpha I yi is equal to 0. Yes? Sorry? We don't have beta anymore. You know, here we realize that beta is alpha I yi xi, and we replace all beta with alpha I yi xi in the original Lagrangian formula. So it's not, yes?
In the Lagrangian, why did it turn into a plus the sum of alpha i's?
Because, you know, this is alpha I times -1. And you have a negative sign in front of that, so it's plus alpha I.
So for that one, should the line above it, should that also be a plus?
This should be plus, yes. Okay, this is a new objective function. I have to maximize this and find alpha. Alpha is my unknown. Y is my labels and X is my data. So alpha is the only unknown here. Okay. Do you know the name of this optimization problem? It's one of the type of mathematical programming. In mathematical programming, you know about linear programming most likely, when you have a linear objective function and set of linear constraint. And you have other type of linear programming, yes?
Quadratic?
It's quadratic programming, yes. Your objective function is quadratic, alpha I, alpha j. So your objective function is quadratic. Your constraints are linear. It's quadratic programming. Quadratic programming is convex problem. So you can solve it efficiently and you can find the global maximum or the global minimum. In this case, you have to find the global maximum. So I can solve this using quadratic programming. And if I do solve this using quadratic programming, I can find beta. And if I can find beta, I can find beta transpose x plus beta null, which is basically my hyperplane. So by solving this optimization problem, I can basically, find alpha, my dual variable, and then find my primal variables. Okay. This is called hard margin support vector machine. Yes?
Why do we want to maximize this?
It's a good point. So we started with minimizing this objective function. Why should I maximize this now? Yes? It's a dual, right? So I'm solving the dual of that problem. It's basically a min-max problem, you know. If you're considering this objective function, in fact, you have to minimize over beta, maximize over alpha, your dual variable. But I rewrite the objective functions in a way that it does not depend on beta, so I just need to maximize for alpha. It's the dual of that problem. It's intuitively, it's like you want to find this minimum, but instead you find the maximum of this one. Okay. Okay. Just why we call it support vector machine? Let me just explain why we call it a support vector machine and show you some important properties here. So in optimization, I think you are familiar with KKT conditions. You know, if say f of x, suppose that you want to minimize f of x, subject to the constraint that gix is greater than equal 0. The necessary conditions for x stars, let me write it this way, the necessary conditions for x star to be the optimal point x star, if x star wants to be the optimal point of this optimization problem, it should satisfy 4 conditions that we call it KKT conditions. The first condition is called stationarity condition, means that derivative of Lagrangian with respect to primal variable at optimal point should be 0. And we have to make sure that primal feasibility constraint is satisfied. Primal feasibility constraint means that our primal constraint at optimal point satisfied, doesn't violate it. Means gi at x star should be greater than equal 0. And it should satisfy dual feasibility. And dual feasibility means my dual variable, which could be, say, for example, alpha I, if I write the Lagrangian for this, should be greater than equal 0. And I have the fourth condition, which is called complementary slackness. At optimal point, dual variable times primal constraint is equal to 0. Okay, we started by taking derivative of Lagrangian with respect to our primal variables and set them to 0. So this is satisfied. And we have this constraint, But what does complementary slackness tell us? If I apply this complementary slackness to our problem here, this is my dual variable. And the primal constraint that I had was that yi beta transpose xi plus beta null minus 1 should be 0 at optimal point. Okay, now if alpha I is greater than 0, because I know alpha I could be 0 or could be greater than 0. It can't be negative because it's my Lagrange multiplier. So alpha I is greater than equals 0. In the case that alpha I is greater than 0, what can I conclude? According to this, yes.
yi times what's in parentheses minus 1.
This bracket is equal to 0, right? Because I have to satisfy this condition. So if alpha I is greater than 0, it means yi times beta transpose xi plus beta null minus 1 is equal to 0, or this is equal to 1. If yi beta transpose xi plus beta null is equal to 1, what can I say about xi? You know, I know for all xi's, this is greater than equal 0, greater than equal 1. That's my constraint here. For any point, this is greater than equal 1. Now, I tell you that for this particular point, which has an alpha I greater than 0, this is equal to 1. It's not greater than 1. What can I say about xi? Yes?
It's the closest point to the origin.
Exactly. That's the closest point to the hyperplane, right? In fact, it is on the margin, because the closest point to the hyperplane, the distance of closest point to the hyperplane is margin. So it means this particular point is on the margin. So it means xi is on the margin. This point, the points that are on the margin, called support vectors. So support vectors are those points that their alpha is greater than 0. And those points are on the margin. So what if this bracket is equal to 0? If this bracket is not equal to 0. So if yi times beta transpose xi plus beta null is greater than 1. When I say that this bracket is not equal to 0, it means it's greater than 1, right? If it's greater than 1, then I can conclude alpha I is equal to 0. So when it's greater than 1 means this point is off margin. It's not on the margin. Any point that's off margin, is not on the margin, corresponding alpha for that point is 0. Only points that are on the margin have an alpha which is greater than 0. It's non-zero points. So interestingly, I mean, it means that alpha is sparse. There are many zeros there. So it means that if I want to solve this, for example, this problem, there are points that are on the margin. There are points that are on the margin here. Okay. I have this point on the margin. I have this point on the margin. And these points, for example, on the margin. Only these few points that are on the margin have an alpha I which is greater than 0. Any other point that are off margin, their alpha I is equal to 0. If their alpha is equal to 0, it means they have no effect in this optimization problem. You know, when I want to maximize alphas that are equal to 0 have no effect here. Only points that are on the margin affect the hyperplane. It doesn't matter if I add a point here or if I add a point here, add a point here. They do not affect this hyperplane because their corresponding alpha is equal to 0. They have no effect. That's one of the reasons that support vector machine, the decision boundary is quite robust in terms of outliers. If I have any point far from the hyperplane, they have no effect. Only points that are close to hyperplane affect this hyperplane. Adding point, removing point has no effect on it. Okay, so only support vectors have effect. Okay, so we know how to solve for beta. How can I solve for beta null? Beta is alpha I, yi, xi, so I can solve for, knowing alpha, I can solve for beta, I can find beta. Any idea how can I find beta null? Yes.
Maybe you could try using a support vector.
Okay.
Since you can calculate beta, you know yi, you know xi. I don't know.
Exactly, that's a good point. I have alpha, this is my solution, my dual solution. Some of them are 0, some of them are not 0. For those that are not 0, I know yi beta transpose xi plus beta null is equal to 1, right? And I know beta, I can find beta null, right? So, So knowing alpha i's, we can find beta as I equal 1 to n, alpha I, yi, xi. Choose alpha i's greater than 0, then for those points, yi beta transpose xi plus beta null is equal to 1. So solve for beta null. Okay. For your assignment, you have to implement support vector machine, but you can use a built-in function in MATLAB for solving quadratic programming. So you don't need to implement quadratic programming solver yourself. But you cannot use built-in functions for support vector machine in MATLAB. So if you want to use that function, maybe it's easier to write it in matrix form. You have x, which is d by n, and you have y, which is your label. It's a vector of n by n, 1. Now I can write everything in matrix form. I have to maximize this. Sigma alpha I. I can define a vector of 1s. Let me call it E. So it's n by n vector, 1, 1, 1, 1, 1. So sigma alpha I would be simply alpha transpose E. Right? And then I have alpha I, alpha j, yi, yj, xi transpose xj. You can think of this part, yi, yj, xi transpose xj. You can think that yi has been multiplied by xi, yj has been multiplied by xj, and then these two, and then we compute the dot product between them. As if I apply the label of each point to that point. So if the label is negative, just I put a minus sign for all features of that point. If it's positive, I don't change it. So basically, I can define x and point-wise product with y. Each data point will be multiplied by the corresponding label of that point. Okay. So then I can basically, define a matrix S, which is x dot y transpose times x dot y transpose. This is going to be this part, and then I have to multiply by alpha I and alpha j, so it's going to be alpha transpose S alpha. And it has all a 1/2 as well. Then I have to make sure that alpha, vector of alpha, is greater than equal 0. And I have to make sure that alpha I yi is equal to 0 in matrix form. It means that alpha transpose y is equal to 0. Now you can pass this to quadratic programming solver of MATLAB or R or whatever, Python, any package that you use, you just pass these matrices to that solver. And it can find alpha, and then you can find beta and beta null for that. Okay, any question? Yes?
So what benefit we get from solving the dual instead of directly solving the primal? I think the primal is also
Quadratic, yes. Yeah, you're right. That's also quadratic. It's an easier problem to solve. It's a sparse problem. That one is not. I mean, the solution here, alpha is sparse, has many zeros, but beta is not. But yeah, you are right. The primal problem is also quadratic. We are going to see the case that data is not linearly separable. And you can appreciate this dual form better in that case. Okay, there are two more things to be addressed. One is that we assume that data is linearly separable. Why if the data is not linearly separable? Okay. Another thing is that this is just a linear classifier, a linear decision boundary. What if the decision boundary is not linear? Can I solve for a nonlinear decision boundary? Okay. So let me start by solving for nonlinear decision boundary. How many of you are familiar with the concept of kernel? Okay. There is an interesting, actually, concept which we can use to make linear algorithms nonlinear. Okay. Suppose that I have this data set. These are plus points. This is one class. And I have another class here. Okay. There is no linear decision boundary here. True? And the decision boundary has this circular shape. This is, suppose that this is a negative signs, and the positives are right at the middle of them. It's in 2 dimensions. Now, if I give you the 3rd dimension, such that all of these positive points are here in the 3rd dimension, then you can separate them linearly, right? So imagine that you have a creature in 2-dimensional. We are 3-dimensional creatures. Suppose that there's a 2-dimensional creature. This is a prison for this 2-dimensional creature. I can put this creature here. She cannot escape. But if I magically give the 3rd dimension to this, from the 3rd dimension, it can escape from this prison. We are, if we lock the door of this room, we are locked here in this 3 dimension. It's hard to imagine, but if there is a 4th dimension, we can escape from this room from the 4th dimension, right? So the same concept in 2 dimension. The only way to separate them is nonlinear. If magically I create a 3rd dimension, then through this 3rd dimension, there's a linear separation between them. Basically, all of these points can escape from this circular prison that they are in it, come out. So the fact is that if you increase the dimensionality of data, then some of the nonlinearity may go away. That was the example that I showed you. Okay. So in 2-dimensional, this is in the geometry of data in 2-dimensional space. In 3 dimension, I may have a linear hyperplane which can separate this data. If the coordinate of points in 2 dimension are x1 and x2, if I map them to 3-dimensional space using this function phi, x1 squared, x2 squared, square root of 2x1, x2, then that would be the geometry of data, okay, which can be separated by a linear hyperplane. Okay, the moral is, if you go to higher dimensional space, you may get rid of some nonlinearity of the data. So you don't have nonlinear algorithm, it doesn't matter. Reshape your data instead of reshaping your algorithm. I don't know how to solve the problem in a nonlinear case. I change my data instead of changing my algorithm. I go to higher dimensional space. Now in higher dimensional space, I can solve for this linear hyperplane. Okay, what the problem is? The problem is that this phi wants to take data from low dimensional space or lower dimensional space, taking them to higher dimensional space. And we know that there's a problem called curse of dimensionality. We have a statistical curse of dimensionality. We have computational curse of dimensionality. Learning in high dimensional space is hard. If you want to learn a parameter in 2-dimensional space and you add to the dimensionality, the number of points that you need to learn the parameters exponentially grow. Okay, it's hard. So there's something good here, but there's something bad also. Computationally the problem is going to be harder. Statistically it's going to be harder. But kernel method is a way to use the less of this dimensionality, but get rid of the curse. Basically, kernel methods basically, there are functions which is called kernel functions. There are functions that if you apply that function in the original space on data, it's the same as applying some phi to the points and then compute the dot product of points. Okay. So there are functions which is called kernel functions, and there are many of them. So if I apply k to x and y, it's as if I mapped x through phi, and I mapped y using phi, and then I computed dot product between them. There are many functions that have this property. Any function that satisfies Mercer condition, or any function which is basically positive semi-definite, has this property. I may not know what the phi is, but as long as I know this function is a kernel function, I know there exists such a phi, even if I don't know what that phi is. Okay? These are examples of 3 kernel functions. A linear kernel function is just dot product between 2 points. And there's polynomial kernel function. You know, if you compute 1 plus dot product between xi and xj to the power of some point, there exists some phi that is this is equivalent to the kernel, to dot product of that phi. And this is called RBF, or Gaussian kernel. So if I compute e to the power of minus xi minus xj divided by some lambda, it's equal to some phi applied to x and to y, and find that product. Okay? In this case, actually, this phi is going to be infinite dimensional long. So, I mean, these points basically are mapped to some Hilbert space, so may not be finite. So the idea for nonlinear case is that we are going to apply phi to data, but not explicitly, implicitly. The data goes to some higher dimensional space. The decision boundary between points are linear now. Then solve support vector machine in this new space. How can I use this property? You know, look at my objective function. My objective function is alpha I minus 1/2 alpha ij, alpha I, alpha j, yi, yj, xi transpose xj. Okay? This is, suppose that the boundary is nonlinear, and I map everything through a phi. So this xi transpose xj is going to be phi xi transpose phi xj. But I don't need to know phi, because I know this dot product is equivalent to a kernel. So basically, I can replace any place that I have a dot product with a kernel. That's it. The boundary becomes nonlinear now. So you're solving here. So just in your objective function, instead of xi transpose xj, put kxi xj. See, for example, using this kernel, RBF kernel. That's it. Okay, let me show you an example. You know, this is the data point that we used before, and you work with the handwritten digits 2 and handwritten digits 3. So this is 64 by 400 data point. The first 200 are 2s, and the second 200s are 3s. So to be able to visualize them using PCA, I map everything to 2-dimensional, and then I apply support vector machine to it. Okay, so in basically x bar is going to be mean of x times a vector of one of length 100. So I repeat the mean 400 times. And I just subtract this mean from the data. I just want to do SVM, singular value decomposition. I want to do PCA on this. So Y is going to be the first two column of U transpose times X tilde. That's going to be my two-dimensional representation if I apply PCA to this data. Okay. Now, in this two-dimensional space, I want to apply a support vector machine to classify points, 2s versus 3s. Okay. So let me call this data. So I have 400 points. I make a part of that train and a part of that test. You know, I am going just to use this function. Cross, this is a built-in function. So it takes, actually I didn't make Y yet. So let me make Y. Y is my labels. So I put the first 200 zeros and the next 200 ones, because the first 200 are 2s, the second 200 are 3s. And then this just gives me indices randomly for some of the points to be my training set and some of the points to be my test set. Now, there is this built-in function, SVM train. So I can make I can say SVM structure, this is just a name, is equal to SVM train, my data set, the training part of my data set, data train, and my label for the training part, okay? And these are parameters of this function, show plot and true. It shows the decision boundary, okay? Okay. This is basically the decision boundary between two digits in the training set. Those points that are have a circle around them, they are support vectors. This case is not linearly separable. You know, you can see that some points are violating the decision boundary. Some red points are in this side, some blue points or green points are on the other side. Okay? But this is linear decision boundary. If I solve the exact problem, just change X transpose X with this kernel in my objective function. That's the only change that I do. So so here I just say kernel function is RBF. Then this is my decision boundary. See, it's not linear anymore. I can find, you know, this nonlinear function corresponding to a linear decision boundary is higher dimensional space. But when you project it in lower dimensional space, it's not linear anymore. Okay, it's nonlinear. And if I change the kernel function to another type of kernel function, then the shape of this decision boundary would be different. So it's RBF, it could be polynomial. See, it's a different decision boundary. Any question here? Yes.
Like the same thing we did for the approximation of QDA from NDA. We increased the dimension.
I can't hear you, sir.
It's the same thing that we did for the QDA to approximate NDA to
Mhm.
approximate QDA.
In QDA, we explicitly computed phi, right? It was explicit. Here is implicit. We don't know phi.
But we wanted to approximate QDA with LDA. We increased the dimension by something.
True.
We used LDA.
That's true. But in that case, we explicitly apply a phi to data. We augment the data. Here we don't. We don't augment the data. We just, you have x. You have x, which is d by n, x1 to xn, and I just compute e to the power of xi minus xj squared divided by some lambda, and this is my k, xi, and xj. So basically, I make n by n matrix here, such that this is kernel between x1 and x1, this is x1 and x2, and so on. And then I replace this k here after multiplying by y. I just replace it here. That's it. Go on.
This is something that is shown that if you add, there is an upper space that for sure the boundary is linear.
No, we don't know that. We have the hope. We hope that in higher dimensional space, data is less complex. But we don't know if it exists. Right? Now let's look at the case that the problem is not linearly separable. So if data is not linearly separable, this is called soft margin. SVM. So in hard margin SVM, I had this optimization problem. Subject to the constraint that yi beta transpose xi plus beta null is greater than equal 1. So I had a decision boundary, I had a margin, and all positive points were here, and negative points were here. So basically, since it was linearly separable, I could find a hyperplane such that any point has at least one unit away from the hyperplane. Now my case is not linearly separable anymore. If it's not linearly separable, means I don't have this configuration. Means there are points that are going to cross this margin, even cross the hyperplane, go to the other side, right? Means that there are plus that may come here. There are minus that may come here. There are plus that go over this margin, or minus that are coming here. So it means this constraint is not valid anymore. I can't say that for all points it's greater than equal 1 because there are points which are going to violate the constraint. How can I change this constraint to represent this case that some points are going to cross this margin? This is not true that it's going to be greater than equal 1. What can I do about it? Any idea? Yes?
Instead of making it a constraint, could we just move it up to the meta function?
Move it to the objective function and make it penalty. It means for many points it should be satisfied. Yeah, we can do that. I mean, logically we can do that. But that's the way that it has been handled, its support vector machine. It's not greater than equal 1, but it's greater than equal 1 minus some value, some small value, right? It is greater than 1 for some point, but some of the points coming here, so it's not greater than 1. It's greater than 1 minus psi. And this is a positive number. Or could be 0. It's not a negative number. These are the points that are going to violate the constraint. But if I change my constraint this way, all points can violate the constraint. You know, I'm allowing points to be not over the margin, but inside the margin. Somehow, I shouldn't allow all points to violate the margin. So somehow, I have to restrict the number of points that are going over the margin. Okay? So I'm going to add a penalty here. So I let some of the points to cross the margin to violate the constraint, but I'm going to penalize them. So since I want to minimize this, if many points go and cross the margin, this term becomes large. And I don't want this to happen. I'm minimizing this. So I'm not allowing all points to violate the margin. Does it make sense? Okay, that's the neo-objective function, neo-constraint that I want to solve. Okay? So I can do whatever I did before. Means I can write the Lagrangian and just look at the KKT conditions and so on. So it's, the Lagrangian, which is a function of beta and beta null, and some dual variable alpha, and they have a new primal variable. Okay, and for this new primal variable, I'm going to need a dual variable as well. So this is going to be my 1/2 beta squared plus gamma alpha I then minus some alpha I, this constraint, minus 1 plus psi I. Okay, and I need a dual variable for this one, minus lambda I psi I. Okay. With the constraint that alpha is greater than 0 and lambda I is greater than equal to 0. Does it make sense? Okay.